Taylor series. Objectives. By the end of this lesson, you should be able to define a Taylor series, recite the Taylor series for sine x, cosine x, e to the x, arctangent x, and 1 over 1 minus x. Use the known Taylor series to evaluate limits, derivatives, and find other Taylor series, and solve AP free response questions on Taylor series. Let's start by defining a Taylor series. If we have a function f of x that is differentiable infinitely many times in some interval around the x value a, then the Taylor series centered at a for the function f of x is given by, so the series notation or the summation notation is the sum from n equals 1 to infinity of the nth derivative of f at a over n factorial times x minus a to the n. And this should look familiar. What we're doing now is expanding upon the notion of a Taylor polynomial. So instead of being a polynomial with finitely many terms, now we're going to have infinitely many terms. So we have f of a plus f prime of a over 1 factorial times x minus a. And when we have the second derivative, we need to have 2 factorial and x minus a squared until we have the nth derivative of f at a over n factorial x minus a to the n, but now we have plus and we have this ellipses because we're going on forever now, because this is a series, an infinite series that's going to go on forever. If a equals 0, then we call the series a Maclaurin series. So again, that mirrors our Maclaurin polynomials in relation to our Taylor polynomials. And the note that I want to point out here is that a Taylor series is just a special case of a power series, where the generic c sub n is now the nth derivative of f at a over n factorial. So this Taylor series here represents a function exactly now, just as a power series does, instead of an approximation that went with a Taylor polynomial. So a Taylor series is going to represent a function exactly over a particular interval, that interval of convergence.
Alright, so here are some Taylor series you need to know, and they're going to look really familiar because they're exactly the Taylor polynomials except that they are series, so they go on forever. So the Taylor series for e to the x, so e to the x is exactly 1 plus x squared over 2 factorial and so on. So the general term is x to the n over n factorial, but this is a series, so this goes on forever. So the only difference between the series and the polynomial is that the series is infinite. It goes on forever. So sine x is exactly x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So that pattern is they're going to alternate, and for sine x, all the degrees have to be odd degrees over their respective factorials. For cosine, cosine is exactly 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial and so on, where for cosine, each of the exponents have to be even. Arctangent is x minus x cubed over 3 plus x to the 5th over 5 and so on, where it's almost the same as the sine one, except that there are not factorials in the denominator, just the individual numbers. And then finally, 1 over 1 minus x is 1 plus x squared plus dot 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 up to x to the n, and it goes on forever. So these are Taylor series you need to know, but it's really just the Taylor polynomials with the ellipses that indicates that this goes on and on forever. And these are exactly representative of each of their respective functions. Alright, so here we want to compute the limit as x approaches 0 of sine x over x using the Maclaurin polynomial. So we should already know that this limit equals 1. So this is one of those trig limits that was just given to us that we needed to memorize. But now we can actually prove this using Maclaurin polynomials. So Maclaurin is in because the sine function is centered at 0. So here, let's go ahead and rewrite the numerator using the Taylor series expansion. So sine x over x is going to be the limit as x approaches 0. So the sine function starts with x, and then it's minus x cubed over 3 factorial, which is 6, plus x to the 5th over 5 factorial, which is 120, minus and so on and so forth, divided by x. So now let's go ahead and simplify this. This is the limit as x approaches 0. Well, there's only one thing on the bottom, so each thing on the top goes over that one thing on the bottom. So this is like x over x minus, and then I have, this is like 1/6 x cubed over x plus 1 over 120 x to the 5th over x, and so on. So now this is the limit as x approaches 0 of 1, x over x is 1, minus 1/6 x squared. So the x cubed over x will reduce down to x squared, plus 1 over 120 x to the 4th, and so on. So now, as x approaches 0, we can use direct substitution. So if I substitute 0 in for every x, which will be in every term except for the first one, all of these pieces are going to end up being 0. So in other words, I'm going to have, so the limit will be gone here. This is just going to be 1 minus 1/6 times 0 squared plus 1 over 120 times 0 to the 4th plus a bunch of zeros. So the final answer is just going to be 1, as we already knew that it was, but now we were able to prove that the limit as x approaches 0 of sine x over x is 1 using the Taylor series expansion for sine x. Alright, now let's show that the derivative of sine x is cosine x using Maclaurin polynomials. So let's start out with the derivative of sine x, which is the derivative with respect to x of the expansion x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So now let's apply the derivative. Since we're doing all these terms are being added and subtracted, we could do each one separately. So the derivative of x is just 1. And now the derivative of x cubed, so remember, 3 factorial is like 1 over 3 factorial, so let's put that in the front. So I have 1 over 3 factorial in the front. The derivative of 3x, or x cubed, is 3x squared. And then plus 1 over 5 factorial. The derivative of x to the 5th is 5x to the 4th. And we'll go one more, minus 1 over 7 factorial. The derivative of x to the 7th is 7x to the 6th, and so on and so forth. So this is 1 minus. Alright, so here's 3 factorial, but there's a 3 on top. So 3 factorial, which is like 3 times 2 times 1. So if I cancel the 3 on top with this 3 on the bottom, then what I have left is x squared over 2 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. So this 5 on the top will cancel with this 5. So what I have left in the denominator is a 4 factorial, and on the top I have x to the 4th. So now hopefully you can see the pattern that this 7 factorial will turn into a 6 factorial because the 7's will cancel, and then I have my x to the 6th on the top. So there's my alternating representation of the cosine Taylor series. So the derivative of sine we just showed using Maclaurin polynomials, or Maclaurin series, Taylor series, is exactly cosine x. So that's probably what that should have said, using a Maclaurin series or a Taylor series.
Now let's move on to some AP Taylor series. So sorry about how blurry some of the questions are. I just copied and pasted them from old AP exams. So on this first one, we're going to let f be the function given by f of x equals e to the negative x squared. In part A, we're asked to write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 0. So we have e to the negative x squared as our function for f of x, and we do know the Taylor series for e to the x about x equals 0. So that's what we're going to start off with for part A. We are going to remember that the Taylor series for e to the x is 1 plus x over 1 factorial, and then x squared over 2 factorial, all the way up to x to the n over n factorial is the general term. And again, it continues because this is an infinite series. So if I'm interested in e to the negative x squared, in place of x, we are going to replace our value of x with negative x squared. So for every x in the Taylor series expansion, we are going to replace it with negative x squared. So e to the negative x squared Well, 1 doesn't have any x's in it, so that's not affected. So we're going to do 1 plus, and then we're going to replace this x with a negative x squared over 1 factorial. And then plus, we have negative x squared over 2 factorial. And we're going to go one further. We're going to put negative x squared cubed over 3 factorial. So those are the first 4 non-zero terms. So 1 is not 0, so that counts as a non-zero term. So here we have the first 4 non-zero terms plus the general term. So we're going to again replace the x with negative x squared to the n over n factorial. And now let's just go in and talk about a few things as far as simplifying on the AP exam goes. Right now, this answer is perfectly acceptable as the final answer, and this is where I would recommend that you stop. Because if you do try to continue to simplify and make an algebra mistake, you would lose points. So in other words, let's say you thought that you should add these exponents instead of multiply them. That would be incorrect. We multiply these exponents, so it would be an x to the 6th in the exponent. But if you made the simple mistake of adding and saying x to the 5th, you would lose the point. So I would go ahead and leave it like this. Here, though, make sure that when we did replace the x with the entire negative x squared portion, that we did keep that quantity inside of parentheses. But then there's no need past there to continue to simplify. So now let's go ahead and move on to part B. So for part B, use your answer to part A to find the limit as x approaches 0 of 1 minus x squared minus f of x all over x to the 4th. So let's go ahead and write the limit that we're trying to solve. So the limit as x approaches 0 of 1 minus x squared minus f of x all over x to the 4th. So let's remember that e to the negative x squared was called f of x. So this portion of the numerator is equivalent to this Taylor series expansion. So let's try to think about that for a second. Let's rewrite the limit as x approaches 0 of 1 minus x squared minus, and now this expansion would go in place of the function f of x. So the first term of the expansion is 1, and then now we can go ahead and think about doing a little bit of simplifying here. So here, this is just negative x squared over 1 factorial, which is 1. So the second term is negative x squared. And then we're going to have plus x to the 4th. I'm still going to leave it over 2 factorial. And my terms are going to alternate. This negative is being cubed, so we're going to have negative x to the 6th over 3 factorial, and so on. So it wasn't even really necessary to simplify. We're just going to have to convince ourselves of what happens as x approaches 0 in this particular limit. So now I've written a few terms of the series, and then all of this is over x to the 4th. So now, let's go ahead and make a little bit of space here. Let's see what happens. So the 1 and the 1 are going to cancel because this negative here distributes. So I'm going to have 1 minus x squared minus 1 plus x squared. So now you can see the x squared terms are going to cancel. And then minus x to the 4th over 2 factorial plus x to the 6th over 3 factorial, and so on. And then we're going to have all over x to the 4th. So quite a bit cancels. So we're still solving this limit as x approaches 0. So let's go ahead and cancel out the 1's, 1 minus 1, negative x squared plus x squared. And then hopefully you can see that this first term here, we're going to have negative x to the 4th over 2 factorial and then over x to the 4th. So the x to the 4ths are going to cancel as well, and all we're going to be left with is a negative 1 over 2 factorial for the first term. And then the next term, we're going to have, if I have an x to the 6th on the top and an x to the 4th on the bottom in the denominator, that's going to simplify to x squared over 3 factorial. And then minus, well, the terms after this are all going to have x's in them. So my next term in the series would have been, negative x to the 8th, and then over 4 factorial. So over here, we are going to have an x to the 4th, or just an x. In other words, all it matters is if there's an x in it, it is eventually going to go away when I evaluate the limit. If any term has an x in it in the numerator, as x approaches 0, because we're still trying to solve this limit, as x approaches 0, all of these terms with x's are going to go to 0. So all that's left is for the constant in front, which is negative 1/2. So the answer to this limit is negative 1/2. Alright, let's try another AP question. Let f of x equal the natural log of the quantity 1 plus x cubed. In part A, we're told the Maclaurin series for the natural log of 1 plus x is x minus x squared over 2 plus x cubed over 3, and we're given the general term for natural log of 1 plus x. And we're going to use this series to write the first 4 non-zero terms and the general term of the Maclaurin series for f. So again, this is going to be a substitution into the given Maclaurin series this time. So in the previous example, we needed to have memorized the Maclaurin series for e to the x. Here we're given the Maclaurin series for natural log of 1 plus x, and we're going to substitute our x cubed into our x, which means it goes into every x in the Maclaurin series expansion. So for part A, let's go ahead and write that the natural log of 1 plus x cubed equals, so I'm going to replace every x with x cubed. So we're going to have x cubed as my first term minus x cubed squared over 2, and then plus x cubed over 3 minus x cubed to the 4th over 4. So there are my first 4 non-zero terms. Again, no need to simplify the exponents. And then plus, and now we're going to have to go to my general term. So we keep the alternating piece, negative 1 to the n plus 1, and replace my x with x cubed to the n over n. And then we have to make sure that it does keep going on, because this is also going to be a Maclaurin series. So this is an infinite series expansion of natural log of 1 plus x cubed. Now let's move on to part B. We're told that the radius of convergence of the Maclaurin series for f is 1. Determine the interval of convergence. Show the work that leads to your answer. So we're already told the radius of convergence for the Maclaurin series for f of x, and that is 1. Now, since this is a Maclaurin series, we know that the center of the series is 0. So if the radius of convergence is 1, then our possibilities for the interval of convergence are negative 1 to 1, and we have open parentheses at the endpoints, or we can have closed parentheses on one side, so we can have a half open interval, so we can have the opposite happening, closed around 1, or we could include both endpoints. This is what we're checking. We don't know which of these 4 options the interval of convergence is. So there's no need to go about performing a ratio test. In this first sentence, we're given all the information we need to find at least the interval of convergence minus the endpoint. So that's the part that we're being asked to test here for finding the complete interval of convergence. So remember that these are x values, right? So x values in these intervals from negative 1 to 1. So what I'm going to do is rewrite the natural log of 1 plus x cubed in its summation notation form. So we're going to have from n equals 1 to infinity of the general term. So we already have the general term written out. That's negative 1 to the n plus 1, and then x to the 3n over n. So this is going to be my condensed version of the Taylor series for natural log of 1 plus x cubed, or Maclaurin, because it's centered at 0. So what I need to check is what happens specifically to the series when I replace the x value with +1 and -1. So let's go ahead and see what happens when I try x equals -1. So my series is going to become the sum from n equals 1 to infinity of -1 to the n plus 1. And now I'm going to have -1 to the 3n all over n. So let's try to think about this numerator here. -1 to the n plus 1 times -1 to the 3n. Well, if I have the same base, I would add the exponent. So this is really the series from n equals 1 to infinity. If I add these exponents, I'm going to have -1 to the 4n plus 1 over n. And so now let's think about, as I substitute in values for n into this exponent here, if I substitute in a 1, I'm going to get a 5. -1 to an odd exponent is still -1. If I plug in 2, 2 times 4 is 8 plus 1 is 9. And then I'm going to get 13 and 17. So all of those numbers in the exponent are going to be odd. And -1 to an odd exponent is -1. So this is the sum of just -1 over n, which if I pull out the negative to the front, because I can pull out that coefficient of -1, so that this is +1 over n, hopefully we recognize this as the harmonic series, which we know to diverge. So since this series diverges by, the nth term test, or we can say because this is harmonic, we know that the value that we originally substituted in, -1, is not part of the interval of convergence. So this power series here does not converge at x equals -1, so that value cannot be in the interval of convergence. So that means we're eliminating these two options that included -1. So now, let's make a little bit more space because we're going to have to test what happens when I substitute in +1. So when I substitute +1 into the x value, I have the sum from n equals 1 to infinity, -1 to the n plus 1, and then I'm going to have a +1 to the 3n over n. So now 1 to the anything is just 1. So it's like this isn't even here. This is just like a 1. So this is -1 to the n plus 1 over n, which is the alternating harmonic series, which we know does converge. So this converges by the alternating series test. So I should have written converges somewhere. So since this converges by the alternating series test, it's the alternating harmonic series, x equals 1 is included in the interval of convergence. So that means it's not this completely open interval, it's this half open interval from -1 to 1, close bracket around 1, open around -1. Alright, next AP problem. We have the function f has a Taylor series about x equals 2 that converges to f for all x in the interval of convergence. So that was already a mouthful. We have some function f. That function has a Taylor series. The center of that Taylor series is 2. And the Taylor series converges for all x in the interval of convergence. So that's just like restating the definition of the interval of convergence. So we kind of have to get through the AP language. The nth derivative of the function f at x equals 2 is given by, so this is a formula for finding the nth derivative at 2. So that formula is n plus 1 factorial over 3 to the n. Whenever n is greater than or equal to 1. So in other words, the first derivative, the second derivative, and so on and so forth. But for the Taylor series, we're also going to need f of 2. So f of 2 is given as 1. So now let's look at part A. We're asked to write the first 4 terms and the general term of the Taylor series for f about x equals 2. So hopefully you're seeing a pattern in these problems. You're often asked to write out the first few terms of a Taylor series and the general term. So some of those problems require you to have a previous Taylor series memorized or just use one that is given. And now in this case, we have to build the Taylor series because we know the general formula. So let's remember that the general formula for the Taylor series is going to be f of a, where a is the center, so f of 2 plus f prime of 2 over 1 factorial, and then x minus a, so a was 2 to the first power, plus the second derivative at 2 over 2 factorial times x minus a squared, plus the third derivative at 2 over 3 factorial over x minus 2 cubed. So this is the first four terms in general. And now the general term, so that would be the nth derivative at 2 over n factorial times x minus a to the n. And now we're going to have to do some substituting. So we cannot stop here and say that this is the final answer. So I do want to clarify when we can stop and we shouldn't do any more work is when we have numerical values everywhere there can be numerical values. So in this case, in other words, we can substitute in our value for f of 2, that is 1, plus f prime of 2 means that I'm finding the first derivative. So the first derivative means I'm going to plug a 1 into this n and a 1 into this n. So 1 plus 1 is 2. So this is 2 factorial divided by 3 to the 1, which is just 3, and then over my 1 factorial, which is just 1, so I'm not going to write that piece. I'm just going to leave it off. And then times x minus 2 plus now f double prime of 2, meaning the second derivative, so this n is a 2 here for the second derivative, so 2 plus 1 is 3, so I'm going to have 3 factorial over, so now here, 3 to the n is 2, right, that was the second derivative, so we're going to have 3 squared over 2 factorial, and then x minus 2 squared. Plus the third derivative of 2, so this n value is 3, so I'm doing 3 plus 1, that's going to be 4 factorial over 3 cubed. Remember, I was taking the third derivative, so 3 goes here, and then over 3 factorial x minus 2 cubed, plus, well, now I need the nth derivative at 2. Well, that's this formula exactly. So we have n plus 1 factorial over 3 to the n over n factorial. So I'm using this n factorial down here. X minus a, or I'm sorry, x minus 2. Our center is 2, so we do want to include the 2 there. X minus 2 to the n. So anywhere that we could have substituted in our values, we did. So we need this general n. And again, I should have been really careful here. This does go on forever, so this does go on forever. So I could substitute into 2 for my center, so I did. I can't leave it as generic a. And then anywhere that I could substitute in numerical values, so f of 2, f prime of 2, f double prime, f triple prime, I substituted in my numerical values, but then notice I didn't bother simplifying them because there's no need to. This is a numerical value, 4 factorial over 3 cubed over 3 factorial. That's a number. We're not going to waste any time simplifying to figure out what that number is. Maybe in a later step that might be necessary, but for now, we leave our answer as this, the way it is for part A. Alright, part B. Find the radius of convergence for the Taylor series for f about x equals 2. Show the work that leads to your answer. So for part B, we're interested in the radius of convergence. So what we're going to do first is we're going to write out the general Taylor series. So remember, the formula is the nth derivative at a. Well, we have that formula. Our a is 2. So our general term looks like n plus 1 factorial over 3 to the n. So that's the nth derivative at a over n factorial times x minus 2, sorry, be specific, x minus 2 to the n. So this is our expansion, our Taylor series for the function f, and if we want to find the radius of convergence, since this is not a geometric series, we're going to have to use the ratio test. Now, before we use the ratio test, I'm going to do some simplifying of the n factorials already. So this first part, n plus 1 factorial over 3 to the n, this is divided by n factorial over 1, which is like multiplying by the reciprocal. And I'm showing all this so we can see that the n factorial, hopefully we've done enough ratio tests to see that the n factorial on the bottom will cancel with the factorial part on the top of n plus 1, so all I have left is the sum from n equals 1 to infinity of n plus 1 over 3 to the n over x minus 2 to the n. So I haven't even applied the ratio test yet, but it's going to be easier to do so now that I've simplified my factorials. So let's go ahead and give ourselves some space here. So now we're going to apply the ratio test. So we're going to have the limit as n approaches infinity of the absolute value of, so we're going to have to substitute n plus 1 in here. So that's going to give me an n plus 2, right? N plus 1 is n plus 2 over 3 to the n plus 1. And then I'm going to have x minus 2 to the n plus 1. And then we're going to need to divide by the original, which is like multiplying by the reciprocal. So let's just go ahead and write that as 3 to the n over n plus 1. So I took the reciprocal of this piece, and now the x minus 2 to the n that was in the numerator would be in the denominator, so I'm going to choose to write it underneath this term. Alright, so I did that so we could see a little bit more clearly how things are going to cancel out. So in order to find the radius of convergence, well, a ratio test tells us that only when this quantity is less than 1, the original series converges. So we need to force this to happen, and now some stuff's going to cancel out, right? 3 to the n plus 1 is 3 to the n times 3, so this is going to cancel, and I'm going to get just a 3 when it cancels with the 3 to the n. And then my x minus 2 to the n will cancel with my x minus 2 to the n plus 1 here to leave me just one copy of x minus 2. So now let's see what we have if we do a little bit more simplifying. Let's see, on the top I have n plus 2. I'm going to put this n plus 1 over here, so I have 3 times n plus 1. And then I have the x minus 2 to the 1 left. So all that is less than 1. So now when I evaluate the limit as n approaches infinity, well, that's only affecting this piece here with n's, not the x minus 2 portion. So as n approaches infinity, since these exponents match, it's going to be my 1 over 3. So what I have is 1/3 times x minus 2, all is less than 1. So now what I can do is I can think about pulling out this 1/3 outside of the absolute value because it's already positive, so I can pull it out, and then I can multiply both sides here by 3 so that I can clear this 1/3. So if I do that, I'm going to get x minus 2 is less than 3. And that tells me that 3 is my radius of convergence. So if we go back to when we first went over radius of convergence, if the center was A, when I ended up with x minus A is less than R, so notice that's what I have. My A is 2, right? That's what my center was. So once I ended up with x minus A is less than a number, well, that number is the radius of convergence. So what I can tell from this is that R equals 3. And that's it for my part B. Part C. Let g be a function satisfying g of 2 equals 3 and g prime of x equals f of x for all x. So the derivative of g equals f. Write the first 4 terms and the general term of the Taylor series for g about x equals 2. So I don't want to get caught up in this notation. Let's focus on what the question is asking us to do, right? The first 4 terms and the general term of the Taylor series for g about x equals 2. So it's very similar to the first problem where we started out really generically, and that's how I'm going to start this problem out as well. Eventually I'm going to need this information, but I don't want you to get really caught up in it and just confused because for right now maybe you don't understand what this relationship means. If I want the Taylor series for g about 2, the formula stays the same even though we change the name of the function. We're going to have g of 2 plus g prime of 2 over 1 factorial times x minus 2. and then plus g double prime of 2 over 2 factorial times x minus 2 squared, plus the third derivative at 2 over 3 factorial times x minus 2 cubed, plus, and then we need the nth derivative at 2 over n factorial times x minus 2 to the n, and so on. So this is a generic way of writing what we're interested in finding, the Taylor series for g about x equals 2, the first four terms, and the general term. So now is where we need to go back and fill in our numerical values when possible. So the first one was given, g of 2 equals 3. So I'm replacing g of 2 with 3. So now I need g prime of 2. So here's where that relationship comes in. G prime of x equals f of x. So if I want g prime of 2, that's really like asking for just f of 2. And then over 1 factorial times x minus 2. So what I'm going to do is go down the line, and I'm going to replace now g double prime of 2 with f prime of 2 over 2 factorial. So this is f prime now. So because if the first derivative of g equals f, then g double prime of x equals f prime of x, taking the derivative of each side. So now times x minus 2 squared, plus the third derivative of g is going to have to be the second derivative of f. So f double prime of 2 over 3 factorial x minus 2 cubed, plus, as I move along, so now here's where we kind of have to recognize the pattern. If I had the third derivative of g, that became the second derivative of f. So if I have the nth derivative of g, when I attempt to use the f function, I'm going to need one less. So I'm going to need the n minus first derivative at 2 over n factorial x minus 2 to the n. And now we have this nth derivative at 2 representation that we can go ahead and substitute in for these different values that we're currently missing. So let's go ahead and do that. Well, our 3 is just 3. And then plus f of 2, well, actually, that was given right here. F of 2 is 1. So 1 times x minus 2 plus f prime of 2. So if I plug in a 1 for n, that's 1 plus 1. So that's 2 factorial over, and then if I plug in 1, it's going to be 3 over, can't forget the 2 factorial that's right here, and then x minus 2 squared plus, now the second derivative, so 2 plus 1, that's 3 factorial over, if I plug in a 2 here, that's 3 squared over 3 factorial, x minus 2 cubed, plus, so that's 1, 2, 3, 4 terms, plus, alright, so now I have the n minus first derivative. So in place of this n, I'm thinking about replacing every n with an n minus 1. So right here where this n is, I'm replacing that with n minus 1, and then this with n minus 1. Well, notice right here, n minus 1 plus 1, then minus 1 plus 1 will cancel, so this formula becomes just n factorial over 3 to the n minus 1 over n factorial, and then x minus 2 to the n. Now, I know what you might be thinking, these factorials are going to cancel out. So 2 factorial over 3 divided by 2 factorial, if I multiply by the reciprocal, yes, they do cancel. But should I even bother thinking about that? No, because I've already substituted in numerical values wherever I could, so I should stop and not worry about simplifying. Even if it ends up being something as simple as just adding 1 plus 1, we don't need to worry about doing it. So if you really, really wanted to, every time right now I said we are substituting in a 1 right here, you could have written 1 plus 1 factorial. You didn't even need to write 2 factorial. And sometimes it's worth it to write all of that out just in case we make a tiny algebra mistake. We wouldn't want to lose points for knowing all this calculus by doing a silly algebra mistake. So now let's go ahead and move on to part D. For part D, I needed to make some space. We're being asked, does the Taylor series for G, as defined in part C, converge at x equals -2? Give a reason for your answer. So what we're going to do is we're going to write out the Taylor series for G. So in other words, G is the sum from n equals 1 to infinity of the general term. So the general term here, well, now's the time to do the simplifying. So now the n factorial, as I said, this was like n factorial over 1, which if we multiply by the reciprocal 1 over n factorial, those n factorials will cancel. So in other words, my general term is 1 over 3 to the n minus 1 times x minus 2 to the n. And what we're asked is basically, is -2 in the interval of convergence? Does G converge at -2? So we're going to substitute -2 into our x. So the sum of n equals 1 to infinity of 1 over 3 to the n minus 1. Then we have -2 minus 2 to the n. So -2 minus 2, that's -4 to the n. So the sum of n equals 1 to infinity of -4 to the n over 3 to the n minus 1. So hopefully you can see that this series is geometric. So if I pull out a -4 from the numerator, so we have the sum of n equals 1 to infinity. If I pull out a -4, then I'm going to be left with -4 over 3 to the n minus 1. So because I would have a -4 to the n, and then I could rewrite it as -4 over 3 all to the n minus 1. And now the absolute value of my common ratio r, -4/3, is bigger than 1. So since the common ratio is bigger than 1, by the geometric series test, the series diverges. So if the series diverges, then -2 is not in the interval of convergence. So -2 is not in, whoops, moved a little bit, the interval of convergence. And the reason for your answer is your work, attempting to show or to determine whether or not the series, when x equals -2, is substituted in, and then showing and you specifying what test we use, and the conclusion, since it didn't work, we know -2 is not in the interval of convergence.